Thank you. Mic is on. So it's 31. Is it possible to see the transparency? Yes. So as you remember, we used a lot Galerkin method. Now, this method had several elements in it. One, determination of approximating function. Psi1 in this case, or psi2, etc. functions. And then we are taking this differential equation, d for w dx in fourth power minus rho a omega square w equals 0. Instead of w, say, if I'm talking about one-term approximation, I substitute a1 psi1. Then I substitute it there. I get a1 ei fourth derivative of psi1 minus rho a omega square psi1, and this expression is not 0 usually. Not 0 usually because psi1 is satisfying boundary conditions, but not necessarily the differential equation. Okay? Very, very seldom it does happen that psi1 satisfies both governing differential equation and boundary conditions. So that means that in that case we have been very lucky or very clever. Okay, if we suddenly satisfied both boundary condition and governing differential equation, that means that there was luck or unbelievable cleverness, and we hit the exact solution. Okay? Usually this does not happen. So, therefore, what we obtained here is denoted as epsilon. So this is epsilon, or error. So that is epsilon a1 ei psi1 fourth derivative minus rho a omega square psi1. And does not equal 0. That means this is an error. Now we would like this error not to be seen from the point of view of psi1, as it were. Now that means that so we denote this f phi, yes, so two functions. So that is an inner product. we define as integral between 0 to L, f of x, phi of x dx. Okay, we define such an inner product. So I'm multiplying then epsilon by psi 1. And I'm demanding that z is 0. So that is Galerkin's demand. So he says, yes, epsilon is not 0. But epsilon is perpendicular, so to say, to psi 1. That is what happens. So therefore, what we obtain actually is as follows: is EI psi 1 fourth derivative psi 1 minus rho A, so that is A1, omega square psi 1 psi 1. This equals 0. Once I calculated this inner product, so to say. From here, this is a product of two numbers, product of two expressions, equals 0. A1 and this expression in parentheses. Now A1 does not equal 0, because otherwise W that is approximated as A1 psi 1 would equal 0 identically. Okay? So from here, we are obtaining that the expression in parentheses must be 0. Okay? So that means EI psi 1 fourth derivative psi 1 minus rho A omega square psi 1 equals 0. And this gives us approximation for omega square. This is EI over rho A, psi 1 fourth derivative psi 1, psi 1, psi 1. And we did obtain some functions like psi 1 for psi 1. Okay, so that is psi 1, and this is also psi 1. And let me put at least two boundary conditions. So, look, please. That is simply supported, and that is clamped. Okay, so this is, for simply supported, we found psi minus 2 psi cubed plus psi in fourth power, where psi equals x over L, non-dimensional coordinate. So here we can also find sine pi psi, okay, because it satisfies boundary conditions. And here I think we wrote psi square minus 2 psi cubed plus psi in fourth power. And here can be function sine square pi psi. Okay, these are approximations. So this one. For example, let us check this one. Psi for clamped equals sine square pi psi. So psi 1 at 0 naturally equals 0. First derivative, psi 1 first derivative equals 2 times sine pi psi times cosine pi psi. So at 0, this equals also 0, because there is sine pi psi. then psi 1 at 1 equals 0 because it is sine pi, sine square of pi. And first derivative also equals 0 because there is this sine pi. 2 times sine pi cosine pi. So that also equals 0. Okay, so we found this. Did I assign you to find for clamped simply supported at home or clamped free? Clamped free. Okay, what is the function for clamped free? Say it again, clamped free. Can you tell me? Did you have it as a homework? Yes. Oh, that is for next Monday. Okay, fine. Fine. So that is not yet done. Fine. Now 4. What is our homework set? 16. Okay. So let us use approximation. Psi 1 equals sine square pi psi for clamped beam and approximate omega 1 square. Compare with the exact solution. As well as with approximation of omega 1 square via psi 1 equals psi square minus 2 psi cubed plus psi in fourth power. This part was done by you already, this last part. But you will just do a comparison. So that is first part. Second part. Construct psi 1 for clamped simply supported beam. Okay. So how do we start? If you remember, psi equals a0 plus a1x plus a2x squared plus a3x cubed plus a4x4. Okay. Then I think we take a4 equals, okay, later divide. Then we satisfy boundary conditions. And at the end, we are also writing everything in terms of x over L. And main thing is that x over L in fourth power, we would like to have 1 here, coefficient 1. We divide whatever coefficient A4 comes out to have here 1. Okay, so that will be psi in fourth power plus whatever. Then third, use result of section 2 to obtain approximation for omega 1 square. Compare with the exact solution. Did we write this? Did you write? Okay, now, so what we have actually, just mathematically, In Galerkin method, we have lots of differentiations. And integrations. Is it right? That is what we have. You did it at home, and you saw that you had to differentiate these functions and multiply by each other and then do the integration. So usually this is done by hand. So a long time ago, it was desired that computer would perform such calculations analytically. It would be nice computer to do such an substitution, integration, etc. So that would mean that we have a butler, if you want, or a computer assistant that does our job. Like butler we should take like in parentheses, of course. So probably most of you do know, but not all of you know, that there are such computer systems that are called computer algebra. Okay. There are many programs, and I will just write down that, so most popular ones. That is Maple, so that's the most popular. And Mathematica. Okay, Maple and Mathematica. These are most popular, at least in this country, computer algebra systems. Now, Maple is available in our mechanical engineering computer lab almost everywhere, almost every computer. Mathematica, I think it's available on one or two computers, but I don't know exactly on which one. Also, we did install, I received free allowance to install it. And it was installed, but today we were not able to locate. So I will describe you today, not only for Galerkin method, but for the rest of the course, some computer algebraic systems. So 32 will be, topic 32 will be computer algebra. Okay, so there are some, maybe we don't have to write everything that is written here, but I did prepare some years ago this presentation for usually vibration course, also for buckling course. From the start of electronic calculation, one of the main uses of computers has been for numerical calculation. Before computers appeared on the scene, a calculation usually consisted of a mixture of numerical calculation and algebraic calculations. That means calculation by mathematical formulas. Like Galerkin method is calculation by mathematical formulas. The authors of tables, especially of logarithms, did indeed carry out enormous numerical calculations. Now, simple calculator has allows you to calculate logarithm of any number. But even when I was a student, and naturally before me, there were books, very heavy volumes, maybe 3 times than this book, that contained tables of natural logarithms. And then you also had to interpolate, because there is a 12 and 1201, 1202. But if you have 1215, then you have to interpolate between these two numbers in a table. Okay? The authors of tables, especially of log, indeed carry out enormous numerical calculations. For example, the famous large calculations of the 19th century include a large proportion of formula manipulation. Big formulas. There were very big formulas in some cases, not always, and we had to do calculations with these formulas. Most famous probably is Leverrier's calculation of the orbit of Neptune, which started from the disturbances of orbit of Uranus and which led to the discovery of Neptune. Okay, so this Leverrier did enormous amount of calculations in order to be able to lead to the discovery of Neptune. The most impressive calculation with pencil and paper is also in the field of astronomy. Delany, that is this gentleman, took 10 years to calculate the orbit of Moon and another 10 years to check it. Okay, 10 years. The result is not numerical. It consists, for the most part, of the formula, which by itself occupies all 128 pages of chapter 4 of his book. Okay, he wanted to obtain a formula which allows calculation of the orbit of Moon. 10 years he actually derived this formula, and for another 10 years he checked. By the way, he found 2 mistakes. But he spent 20 years. Just 15 years ago, this calculation was conducted again by Maxima in 1 hour. Maxima is one of the computer algebraic programs. Nowadays, that can be conducted within 15 minutes. Now, what he spent on 20 years of his life. Okay? When computers appeared, numerical calculations were made much easier, and it became common to do enormous calculations, of course. However, numerical calculation does not rule out algebraic calculation. Algebraic calculation has not lost its relevance. Now, in 1953, 2 very important master theses have been conducted. One at Temple University and another at MIT. Look, please. Karimanian, he wrote the thesis, Analytic Differentiation by a Digital Computer. So what he said, he wants a program where you put a function and the computer prints out the formula for the derivative. Okay, that was a long time ago. Even I was a kid, and you guys were not yet in this world. Now, second is Nolan, also analytic differentiation on a digital computer. Okay, so difference here by a digital computer, here on a digital computer. This is May 1953, also May 1953. Okay, these 2 very famous theses, master theses for doing this. Okay, now there are many programs like Mathematica, I did not write Maple, Reduce, Maxima. At the time when I prepared this, they were the most widely available of all large systems. Now there is also Maple. MuMath, easily available on microcomputers. Stretchpad, prototype for the next generation of computer algebra system. Kamal, Altran, etc. There are many programs. Analytic expressions for indefinite integrals, a good deal more reliable than the random undergraduate or graduate. We're talking about randomly chosen. If you choose random undergraduate student or a graduate student, then computer performs that job better than that randomly chosen person. It naturally cannot do a better job than the best graduate student or best undergraduate student. because very often computer says, I can't. It returns request back as it is. Whereas clever undergraduate or graduate student can do some very beautiful substitution and reduce the integral, for example, to something else that is known before. Okay? But it is better than a random undergraduate or a graduate student. Okay, we will look at computer algebra as an algebraic assistant. So there are many books. I listed some books. That means that I prepared it probably this material in 90 or 89. Davenport, computer algebra. Rand, computer algebra in applied mathematics. Reina, reduced software for algebraic computation, etc., etc. There are many, many books. Okay, so there are variables. So we will talk about variables. Now, if you write anything, then instead of reduce, please write maple. Okay, it's the same. I wrote for something that was in much use at that time. As in other computer languages, operations in maple deal with variables and their values. In contrast with more familiar computer languages, variables have values which can not only be numbers but also algebraic expressions. For example, 1234 or 1234 divided by 5679, u plus v, 3 plus angle minus 5x in power 3/4 plus y in power 10. Okay, these two stars means raised to the power. Reduce considers angle or small angle or an, capital GLE, to be the same variable. It doesn't pay any attention whether it is with big letters or small letters, etc. Now, this should be checked every time. When you go to the computer, when you use maple, you'll see there is help, and you will see in the help what is happening. But you can also get some books that are available in the library. This is, for example, Maple 8, okay, by some author. You can write it down if you want. Introduction to Maple 8, David Schwartz. Okay, and that is published, I think, by Prentice Hall. I don't know whether this is the latest edition. I will check which year it is written. Maybe it is not. 2003. I'm sure that is not the latest. This is not the latest. Okay. Now, that will help you very much in not only in this course, but in every other course. You will do calculations analytically on computer. Numbers in Maple are normally integers or quotients of integers. It means whole numbers or fractions, not decimals. The number, say, 13.579 would be represented as 13,579 divided by 1,000. This way, answers are always exact if the original data can be given exactly. There is no round off. There is no limit other than size of the computer memory on how many digits a number can have. The number 10 in power 100 can be handled effortlessly. Even so, it takes 7 lines for reduce to display its value. A variable is given a value by using this assignment symbol. Semicolon and equal. A equals 1, 2, 3, 4. Lambda equals alpha times L. Do you remember alpha times L? Vibration. Or phi equals x in power k. As a general rule, if something you are doing in Maple produces very cryptic error messages, consider the possibility that you have inadvertently used a reserved word. For example, sum. Sum cannot be used because sum is a word that, for example, if you write sum equals sum plus x, resulting in an improper delimiter message, sum is reserved word for the sum construction. For example, cosine x cubed means, if you will write like this, means cosine x cubed. Okay. When in doubt, use parentheses. So if you want cosine x to be cubed, then here should be one more parenthesis, I forgot. Here cosine x, then parentheses here, and cubed. There are built-in functions, say sine, cosine, log, square root, etc. You don't have to define. It is known by the computer, so to say, by this program. It leaves, okay, sometimes it leaves sine a plus b or sine 11/7 unchanged. Does not use summation formula. It does not use often sine a cosine b plus cosine a sine b. Does not do that. Okay, NUM and DEN take a single expression that is for numerator and denominator of the result. For example, you may want to know numerator of x over y squared, okay, or denominator x over y squared divided by 2. So it would give denominator y squared. Numerator, if you write 100 divided by 6, so you would get 50 because it actually divides this by 2 and gets 50. Since 100 over 6 equals 50 over 3. Now differentiations. The function df performs differentiation of expression. For example, what did I do wrong? I probably have to ask some.
Just give it 1 second.
Oh, okay. Thank you. Yes. So if you write e equals x cubed, so e equals x cubed, then if you write df e with respect to x, we will get 3x squared. I think in mathematics department that is taught, is it not? No? You studied at math department. Oh, you were not. Okay. So higher derivatives. So differentiate e with respect to x 2 times. Also can be done partial differentiation. Differentiate x times y with respect to x. Output will be y. If one variable y is to be treated as dependent on another x, then declaration should be made. Depend y upon x. Okay, for example, if we want to differentiate x with respect x times y with respect to x, and then y depends upon x, we will get this result plus y. Okay, so partial derivative y with respect to x 2 times and u and w 2 times. So that is this one. Integration, symbolic integration operation int is available. You just write int. So especially it's very easy to do integration of polynomial expressions that we have in Galerkin method. Because it's polynomials, it's very easy to do all these integrations. So integrate EE with respect to x. The arbitrary constant is not represented. Integrate, say, x in power 10 with respect to x. You will get x in power 11 divided by 11. When int fails to carry out an investigation or a job it is asked to do, it responds as follows. It returns the input int unchanged. It just gives you back your request. And that means that your request has not been fulfilled. The computer does not know how to do this integration. For example, if you ask, integrate sine x divided by x, so that integral is not known, the computer naturally will return the same response. Okay, for example, here we could have for I from 1 to 100, do a equals a plus I squared. Or a equals for I from 1 to 100, sum I squares. So we will get this result. Now you can treat as you wish, but that every time you should check in every language that you are using what is the syntaxes, what is a grammar, so to say, how you should use. I am talking now I prepare this for reduce, but you will check in the computer help or in the book on Maple how it is written in Maple, or if Mathematica, then how it's written in Mathematica. But once you enter the computer, you can see in the help how it is written. You don't have to have a book. Oh, I don't know which language is used because, look please, in Reduce, Fortran was used, but now in Maple, I don't know. But we may ask if a young fellow there knows. Mr. Duja, do you know maybe what programming language is used in Maple? Procedures? Okay, so various procedures are being built, means like functions, appropriate functions associated. Like, for example, in early times, I had to develop myself for my PhD. I remember Bessel function procedure, how to evaluate Bessel functions. So I had to build a special program because it was not available on the computer. So there was no standard program for that. So here there are special procedures built in. That was called a procedure, like sine function here. So that is like each of them is a special procedure. Now there is substitution command, it's very important. SUB function gives a result of replacing every occurrence of a variable in an expression by something else. For example, EE is set x squared plus y squared. So that is it. Then I say F is substitute x equals a plus b in EE. So it will substitute here instead of x, a plus b. So we will get a squared plus 2ab plus b squared plus y squared. Or G, substitute x equals a plus b, y equals y plus 1 in EE. Okay? Now there is a solve function. For example, to solve the set 3x plus 2y equals 36, 2x minus y equals 17. So we just write, we enter solve, then list 3x plus 2y minus 36, 2x minus y minus 17 with respect to x and y. Output will say solution 1, 1 equals 10, solution 1, 2 equals 3. It's very neat. That is, indeed, you feel empowered. I mean, you are a powerful guy. You're asking computer, do this for me, and it does it for you. Or, for example, solve x cubed minus 3 with respect x cubed minus 7, excuse me, with respect to x. That means x cubed minus 7 equals 0. So then it will give you an expression. Solution 1 is cubic root from 7 with minus sign, square root of 3 times I plus 1 divided by 2, minus 1 divided by 2. And then third root is just 7 cubic root from 7. There are 3 roots naturally. Cubic equation has 3 roots. 1 real in this particular case and 2 complex. Okay. Do you find it neat? Now there is also array and operator. Array A10 or B25. You can declare and use 2 and higher dimensional arrays. Array D510. For I from 0 to 10, do BI equals AI. Or for I equals from 0 to 5, do. For J from 0 to 10, do. E of ij equals I plus j. So then it will build a matrix whose elements are A plus j, for example. Okay. Yeah, sometimes there is, in some programs, in some computer algebraic systems, there is float command. The command on float instructs, in this case, reduce to change numerical fractions to floating point numbers, like this. Accurate as this may be, it is not very instructive. So can you imagine you can get such an answer? So it's very uncomfortable. There are very many digits in numerator and denominator. So if you use command on float, then you will get result 209.50151. So it is better we have printed S in a more informative way. So there are some books about reduce, but I'm not going to talk about them. Okay, there are matrices also, like vector for 1, for 4, etc. K, N, for 4. Vector is declared as a column vector. That is as a 4 times 1 matrix. K matrix, with size still not specified. The numbering of elements starts at 1, not 0, as in the case of array. In array, numbering starts with 0. Here it starts with 1. Vector 1, 1, x, for example, x times y squared. Vector 4, 1 equals 25. If the size of matrix has not been specified, the mat operator must be used for assisting values to the elements of L times n matrix in order to let program know what size of the matrix it is. So then it will define matrix, like matrix mat M11, M12, M1n. So it's the first row, M21, M22, M2n, ML1, etc., MLn. So matrix, and then we can assign the values. M11 equals -1, M22, M33, M44 equals 1, etc. So there is, of course, operations of transposition, like transpose TP of n, transpose of matrix, or determinant DT of matrix. For example, determine the eigenvalues of this matrix. So we write matrix M33, MM33, and we will get eigenvalues of this matrix. I recommend that you get, you check out from the library at least one book on Maple. There are, I'm sure, several books, or maybe many books even, on Maple. And check, I don't recommend you to buy any books, but check one book and then use it in order to do this assignment. I assigned you the assignment that I asked you to do on Maple. Let us write it down here. So please, everything here do on Maple. Okay? Everything that was done here, I would like you to do on Maple. Okay? And you will see how beautiful it is to have this computer assistant. Usually, I mean, in many, say in Europe, even in high schools, many high schools are teaching symbolic algebra, and students already know symbolic algebra when they come to the university. At least I know in Austria that is done. Yes. Any questions? So now 33. Duncan functions. So for simply supported beams, we found this psi1, if you remember, polynomial equals xi minus 2 xi cubed plus xi in fourth power. Okay? Now the question is how to obtain higher order. These are called coordinate functions. And we answered this question actually past time. How to obtain functions, second higher order functions. So there is Duncan from England developed such functions. For simply supported beams. And I would like to write down these functions. So psi j plus 1, that is how it says, psi equals, we will check, j plus 3 psi j plus 2 minus 2j plus 5 psi j plus 3, then plus j plus 2 psi j plus 4, j greater than 1. Greater or greater than, okay, let us check if j equals 0. Let us check if j equals 0. Now, j equals 0 will be 3 here, but here we don't have. J equals 0 will be psi squared, and j, no, that will be, let me check which functions are, which Duncan polynomials. Let us check whether this, I rewrote it from my transparency, some transparency, but it did not say. Let us check whether they satisfy boundary conditions or not, or which boundary conditions it satisfies. So that is 7. So naturally psi at psi 0, when xi equals 0, psi equals 0. Okay. Now let us take first derivative. It will be j plus 3, j plus 2, psi j plus 1. So that is psi's first derivative. Minus 2j plus 5, j plus 3, j plus 2, plus j plus 2, j plus 4, sine j plus 3.